On gravitation here. All right, remember the grade sheet, check it. And by the way, you can still turn it, if you didn't turn it in homework a long time ago, you can still turn it in. Okay? So everybody usually gets a perfect homework score, 100% on the homework.
All of the homeworks have to be turned in?
No, I dropped one. So you don't have to turn in one. All right, so gravitation. This sort of quantitatively began in 1665 when Newton proposed this so-called universal law of gravitation. The word universal here means it applies to any object. Okay, and he said there's an attractive force. Okay, gravity is an attractive force. It obeys Newton's third law. The force is equal and opposite. So it's universal. Every pair of bodies, objects, will exert there's an attractive force between them. It's equal and opposite, obeys Newton's third law. And it's given when for point particles, when the spatial extent of these particles is large compared to the distance of separation, so that I can think of them as points and not worry about their structure, it's given by this. It's called an inverse square law. It's inversely proportional to the square of the distance between them. It's proportional to the product of the masses. So if you double either mass, you're going to double the force. That's reasonable. If you double both forces, you quadruple the force, right? And then there's a constant of proportionality here. It's universally, everyone calls it big G, okay, as opposed to little g, which is the acceleration due to gravity on some astronomical body, right? So this is it's the universal constant of gravitation, and it's actually, I think it's the least well-known constant of nature. So what I mean by that is, it's known to so many figures here, and it's the fewest number of figures for I think anything out there. As we'll see, it's difficult to measure this because in the laboratory, gravitational force is really weak, right, between two bodies. You have to. It's very weak. So we'll discuss that towards the end of the lecture. So you'll notice here it falls off with distance, right? It's an inverse square law force. If you double the distance here, you're going to quarter the force. So if I double this distance here, the force is going to drop by a factor of 4. If I increase the distance by a factor of 10, the force will drop by a factor of 100. Okay, it's proportional, inversely proportional to the square of the force, inverse square law of force. A very similar force exists for electric charge. It's called the Coulomb Force. It's an inverse square force. And this is significant for something we're going to talk about later. Okay, I'll remind you. Now, for objects we normally deal with, non-astronomical objects, this force is very weak. All right? So as an example, if we have two 1 kilogram masses a meter apart, the force is going to be, I got 1 kilogram times 1 kilogram divided by 1 meter squared. So in SI units, this is all just going to be 1. And we're going to get a force in newtons equal to the value of G here, big G, which is 6.6 to 3 figures is this value. So this is about roughly 70 piconewtons. A pico, remember, is 10 to the minus 12th. Okay. So I tried to find some way of making this to get a feel for how little this is. For example, this is going to correspond to the weight of some mass in the gravitational field of the Earth, and it's a nanogram. So a nanogram on the surface of the Earth, a nanogram weighs this amount, very roughly, okay? So I tried to find what weighs very roughly a nanogram, and there are things out there, you know, like I think biological things, but it's not going to give us any kind of a feel for it. It's just. I even looked into. And I found mistakes on the internet.
There are mistakes on the internet?
Yeah, wow. So one of them said it's 50,000 carbon atoms. And I said, oh, that's good. You know, carbon 12 is a standard way of mass unit. So I said, oh, that's not bad. And then I realized, no, that seems a little too small, and it's way off. It was way off. Somebody else said it was the weight of a cubic millimeter of water. No, that's way off. Way too much. So anyway, it's really tiny, okay? It's hard to measure, but it has been measured. And people continue to measure it for one of the reasons is fundamental constants. I don't know if you know this, but fundamental constants of nature can be slowly changing over time. And this has like cosmological, has implications for cosmology. So that's one of the reasons people want to accurately measure these constants. But we'll discuss the first accurate measurement towards the end of the lecture. Okay, so the gravitational force is a vector. In particular, it obeys the principle of superposition. Remember the principle of superposition? If I've got a mass here and another mass here, and we focus our attention on this mass, it's going to be attracted. And the force is given by Newton's law of gravitation, right? Now, if I remove this mass and I have another mass over here, there's going to be a force here, right? What happens when both are present? Does the presence of this one alter that force? Ooh. Eric is usually right in a weird kind of way. According to Newton's laws, the answer is no. The presence of this does not alter that force. So in other words, the principle of superposition holds. The net force is simply the vector sum of the individual forces, and they don't interfere with each other. Okay? However, Newton's law of gravitation is just an approximation. An improvement is Einstein's theory of gravitation, which obeys relativity. We'll talk about that on Monday a little bit, right at the end, okay? But Einstein's theory of gravitation is nonlinear. The principle of superposition breaks down. Now, however, this is an extremely good approximation. I don't think anyone has directly measured a breakdown of this for gravity. But in extreme cases, like near a black hole or something like that, the principle of superposition will actually break down. We know this from Einstein's theory. Incidentally, Einstein's theory is only an approximation because it's not quantum mechanical. It's a classical theory. It doesn't behave quantum mechanical. It doesn't, it's not a quantum mechanical theory. And no one has been able to come up with a quantum theory of gravitation that doesn't contradict itself. Weird, huh? So that's one of those instant Nobel Prize things in physics. If you can come up with a quantum theory of gravitation, you should publish it because you'll get the Nobel Prize. All right. So anyway, so this is a long-standing problem. So the Newtonian theory of gravitation is just an approximation. Everything is just an approximation, actually, you know. But it's an extremely good approximation for a broad variety of situations, okay? And it's very difficult to observe a deviation from that. It's very difficult to observe deviations from Newtonian theory. But they've observed some, like, I don't know, the last count, it was like a half dozen or something like that, different experiments. And Einstein's theory of general relativity has held up. Other theories of gravitation have fallen by the wayside. Anyway, that's a whole different story, and I shouldn't be talking about it. So, we assume the principle of superposition here, which is an extremely good approximation in typical situations. So we can have any number of point masses here. We can have some kind of body. Here's a mass of interest here. How am I going to find the net gravitational force? But due to the principal superposition, I'm going to consider a little mass element here. Let's call it Mi. And that's going to attract, there's going to be this little force here due to that. And then what do I have to do to find the total force? One word, starts with I. Integrate, yeah. In general, if it's a discrete collection, it would be a summation. But often, what's relevant is a continuous body. We would then sum over all these little masses, which means we integrate. And when we integrate, this is going to become a differential. We're going to split this up and take the limit. This becomes infinitesimally small, right? And in that case, we replace the mass with the density times the volume. So this is the volume element. The density is the mass per unit volume. So to do integrals, if I want to integrate over all these, we can sum over all these forces here. When we do an integral, we want to make it geometrical, put it on calculus, turn it into a standard, an integral. Mathematical integral. So we get rid of the mass in this way, because the density is the mass per unit volume. So then the integral becomes an integral over this with the universal law of gravitation. This density here, the mass per unit volume, is not necessarily a constant, right? The density of the Earth is not a constant. It increases. On the average, it increases with depth. And we'll talk about that. Look at that in a very dramatic way at the end of the lecture. Okay, so first problem here, Newton's apple problem. Okay, so I don't know if it's established that he really was thinking about apples, right? But it sounds good, and it brings across the point here. So here's an apple, here's the Earth. What's the force of the Earth on the apple? Well, it looks like we have to integrate. And I'll tell you right now, it's not an easy integral, and we're not going to do it. But you will. Are you guys going to take the introductory electromagnetism course, 1322? Okay, you should do it in there. Because remember, the Coulomb force is an inverse square law of force, just like gravity. So there, it's a similar problem arises. You have a sphere of charge, and you have a charge out here, and you want to know the force. You have this uniform sphere of charge, and you want to know the force on another charge. And it can be done more easily if you develop what's called Gauss's law. So you'll be able to see this, but we're not going to prove it in here. It's not done at this level. It's not, and that's a good idea not to do it. Trust me. But we can motivate the result. All right. And in fact, speaking of motivation here, this was one of Newton independently invented integral and differential calculus. I don't know if you guys know that. Yeah, Newton did a lot of things, and one of his motivations to invent integral calculus was just the problem we're talking about here. He wanted to find what's the force here, and at this point, the only way we know how to do it is we'd have to integrate, like I was telling you. We have to do an integral. We have to sum over all the mass in here. So there are two results that allow us to motivate it without actually doing the integral, which, like I said, we're not going to do. And these are sometimes called the uniform spherical shell theorems. So for an inverse square law force, you can prove these two theorems. Okay? And the first one is, and in our case this is for gravitation, but it applies equally to the electric force, Coulomb force. We have a mass outside this uniform spherical shell. You see see here? It says it's italicized, which is supposed to add some emphasis to it, but I know from the laboratory handouts that it doesn't. And the quizzes. And the quizzes, you know, I'll italicize something. Okay, I'm going to make this as important. And you guys just, I don't know what it is. So, you know, I don't know. I don't want to get in this game of emboldening it and then capitalize. You know, it just never ends, right? Maybe you get desensitized to it. Maybe you're desensitized to it. Okay, so anyway, these are the uniform spherical shell, okay? So it's a uniform sphere. The density is the same around here, right? And you have a mass outside. The force on this mass is the same if you imagine all the mass to be concentrated at the center. That's what this says. When you look at this, you say, oh, this is like force between 2 points, M and M, and it's at the center. Okay? So you can prove this by integration. You can prove it by integration, which we're not going to do. The other, it's natural question here, which it has some gravitational consequence, actually, now that I think about it, but it's very important in electrostatics, which you'll study in 1322, is inside the spherical shell here, there's no force. It's got to be a uniform spherical shell, but inside there's no force. And you can kind of see how that can occur here. There's attraction to all of these mass elements over here. There's attraction. There's also attraction here. There's a lot more of these tending to pull it this way than these, but these are closer. And it turns out they exactly cancel each other, and the net force is 0, no matter where it is inside here. So that's important for ancient aliens, because you know that the Earth is hollow, right? And ancient aliens live down there. God, yeah, they still do. Yeah. Is it? Okay. Okay, now again, these can be proved, okay? But I want to make a point of, we're not going to do it here, it's too complicated. But the natural place to do it is in electromagnetism, or specifically what we call electrostatics, where you'll develop Gauss's law, which is a very convenient way of, it includes it holds for an inverse square law force, okay? And then you will look at this and say, of course, with Gauss's law, you'll look at these and it's obvious how to solve these from Gauss's law. But it takes time to develop Gauss's law, but you should do that in 1322. Now I want to remind you, this is only true for a uniform spherical shell. It's easy to find counterexamples. For example, here. Okay, this is like a binary star. Okay, now we're going to do a homework problem, or it's on the quiz. I can't remember. But there's going to be a gravitational force on this mass, right? It's the sum of these gravitational forces here, okay? And it's very easy for students and even some non-students to think that, well, I can just imagine concentrating this mass at the center of mass and then write down, once I got this particle here, I just write down the universal law, right? G, big G, times the product of the masses divided by the square of that distance. This you can show. If you do this properly, sum this gravitational force with that, you'll find that it's not equivalent. You get a different answer when you do that. All right, it's only for a spherical shell. And it's even more, suppose this were inside, between the two. Do you think the force is going to be 0, analogous to what it is for the spherical shell? Obviously not, right? It's only going to be 0 if it's right in the middle. It's going to be 0. If it's over here, which way is the force? There's going to be a force because it's got to point exactly to the right, because this is closer. Okay. So we can now, using this spherical shell theorem, we can solve the Newton's apple problem. Because this is just we're going to assume a perfectly spherical Earth here, all right? And we're going to sum over all the or integrate over all the shells here. Each shell contributes to the force the same if its mass is concentrated at the center. So I can immediately do using the spherical shell theorem, I can immediately integrate this. I can imagine all this mass concentrated there. Now, are we assuming that the density has to be constant here? Anybody? I have these collection of shells, right? The density in each shell has to be constant in each shell. But what about different shells? Does the density have to be the same? No. Right. No, it doesn't. So that's convenient because, like I said, the density of the Earth gets greater, and it's significant as you get down here. And again, we'll talk about that later. So we're okay with that. The density does not have to be constant. It does have to be spherically symmetric, though. If you move at some radius here, the density can't change. Each shell has to, so the density can be at most a function of r. We can have our density here, where this is the magnitude. So we can have a function of r. Each shell will then have the same density, but they don't. For different shells, they can have a different density. But inside each shell, there's the same density. It's just a function of r. Okay, so here's the result. This is the result. We imagine all the mass. As long as we have spherical symmetry, that's the way we say it, physics, spherical symmetry, we can imagine all the mass to be concentrated at the center of mass. That's going to be the gravitational force. And we call this, on the surface of the Earth, we call it, or actually anywhere, we call it the weight. This force here, the gravitational force, as we've seen, is called the weight. If we let this mass go, it's going to accelerate, and so it's going to obey Newton's second law. This will be the force. That will equal the mass times the acceleration. And we have a name for this acceleration, free fall acceleration. We call it g, acceleration due to gravity. So, substituting our force here, we get this. And now you'll notice we can simplify this, right? And this is very important. How can we simplify this? Anybody? We can cancel little m, and that's a big step here. What it's saying is this. That means that in the end here, the acceleration due to gravity for free fall does not involve the mass of the falling body. And what's happening here is this. The force is proportional to the mass, but the inertia is proportional to the mass, okay? Also, and in fact it's equal to the mass. So if we double the mass, we double the force, but we make it twice as hard to accelerate because it has twice the inertia. So they exactly cancel. And the acceleration due to gravity is independent of the mass. Now we've seen this before, but now we have a deeper theory. Now that we have this, we can appreciate it from a deeper perspective. So this is why all objects in a vacuum, in free fall, in a vacuum, have the same acceleration. Remember the penny and the feather? Okay. Now, you may wonder, okay, you have to have a spherically symmetric body. Now, no astronomical body is perfectly spherically symmetric, of course. So there are like 4 effects, at least that I know of, that can cause this relationship here to be just approximate. Okay? So again, let me remind you, we've actually come up here, we have a prediction. You can think of this as a prediction of the acceleration due to gravity. That's the idea of physics, right? We don't have to treat this empirically anymore. We have a theory, but in any theory there are assumptions, right? And here, in this case, it's spherical symmetry. Well, what can violate that spherical symmetry is these 4 things here. First one I have is spin. The fact that typically an astronomical body is spinning is going to affect the acceleration due to gravity. Now remember, the acceleration due to gravity, little g, is, for convenience, it's what you would measure if you imagine doing an experiment. Okay? So I should have brought in a globe, but I have something spinning here. If I drop something at the North Pole here, or on the axis of rotation, how's g going to be affected? What do you think? So we're focusing on the effect of spin. So we're imagining a perfectly spherically symmetric body. We just want to focus on one effect, and that's the fact that it's spinning. How does that affect g here? It doesn't, right? It doesn't. There's actually a very weak general relativistic Einstein theory effect. Extremely weak, though, but not for Newtonian. How about on the equator, though? If I'm on the equator and I release something from rest, am I going to get the same acceleration at the North Pole? This is assuming a perfectly spherically symmetric Earth. The only thing we're including here is the rotation. No. What's G going to be? Is it going to be less or greater than?
Less.
It's going to be less, right? You intuit it. We're going to do a homework problem on this. But you have the right intuition. In fact, you can go to a limiting case. If the Earth is spinning fast enough, and I think this is the calculation we're going to do in the homework, but I can't remember. If the Earth is spinning fast enough and you release something from rest, it's just going to sit there. There's going to be a critical rotation speed of the Earth where it's just going to be in uniform circular motion. The centripetal force is supplied by the law of gravitation, right? So you know that can be happening. You know that you can have an object going uniform circular motion. That's orbital motion, right? So in that case, G is equal to 0. It's not falling. We don't see it as falling. Okay, so spinning, how big is it for the Earth? It's about 1/3% on the equator. And of course, it exists at any other, what's this called? Latitude? I'm just joking. Navy. So it'll exist at any latitude, but it's getting weaker, and it goes to 0 at the poles. It goes to 0 at the poles. What about oblateness? Now this is actually an independent effect here. Oblateness is due to the fact that when the Earth, for example, was created, and we're not going to talk about how the Earth was created, okay? Just a joke. It was molten, very hot, molten. So it wasn't a rigid body, and it was spinning. So what's going to happen? You saw the demonstration. It's oblateness. Remember the hoops spinning? Great demonstration. So then it cools down and it just gets frozen into place here. Now, this is going to have an effect upon G because it's not a sphere. The Earth's not a sphere. And I want to point out that when we look at this error, I actually should remove this because even though the spin caused the oblateness, we want to focus our attention on how G is going to be affected by the oblateness. And there's nothing to do with the spin anymore. We can imagine it not spinning. We can actually, this is this whole idea that I try to get across to you guys in the lab about how you focus on certain sources of error, assuming everything else is perfect, because you want to find what that source of error is going to do. This is the thing that I, in vain, have been trying to get across to you in the lab, right? And some of you are actually, some of you, I can tell, it's partially successful. I don't want to quantify that any further, but it's partially successful. So what is this going to cause? This is not so obvious. This is not so obvious. We're further away here. I'll just give you the answer. G gets less at the equator and it gets greater here. But it's really not obvious. Now you're closer to the center here, but the mass has been spread out. I don't think it's obvious. And it turns out, remarkably, to be very roughly the same order. I shouldn't say remarkably, because it's just the same order of magnitude as this. It's very roughly 1/3%. It's on that level. Finally, I don't know if you know this, but it was a hot topic when I was a kid, because in the early days of satellites, they found that the satellites they were deviating from the predicted trajectories outside the error bars, which you understand now, right? Okay, never mind. And they inferred, okay, that the Earth is pear-shaped. It's fatter in the southern hemisphere than the northern hemisphere. How many people have heard about this? Yeah. Did I mention it before? Yeah, I mentioned it before. Oh, I'm sorry. It's a very weak effect. I don't know what to quantify it. I don't know, but it is there. Okay, and it was discovered. It was inferred from the early satellite days, where the orbits weren't precisely. They were going outside where the uncertainty where they should be going.
I heard they were really caught up in making golf clubs at that time too.
Yeah, some people actually claim that it slowed up that the golf club thing slowed up some of the research on this. It's a joke, right? Okay. I got You know, I may have changed this story over the years. You know how stories change. So I talked to my parents this weekend. I'll ask my father about that, see if he remembers. He may deny it. No, I never did it. I don't know.
I remember. Bring him in as guest speaker next week.
He wants to find right out.
Another one, of course, is that we may not have uniform density. Now remember, as long as it's spherically symmetric, we're okay with that. But you know, like the Himalayas, they're going to throw off the acceleration due to gravity, right? There's a lot of mass there. It's not that much compared to the Earth. It's not going to throw it off a lot, but I'm sure the effect can be measured. Okay, so let's do a calculation here. We now have this formula. We can calculate little g. All right? So here's the Earth. Here's the mass of the Earth. Here's the radius of the Earth. This is actually the mean value. And we're going to compare it to Jupiter. Jupiter is 318 Earth masses. We're going to do this to 3 figures. You'll see why. The diameter of Jupiter is this. Okay, so on Earth, on the surface of the Earth, here's our formula. Big G times the mass of the Earth divided by the square of the radius of the Earth. We plug the numbers in. Into 3 figures here, we get 9.83 meters per second squared, which you know is not bad, right? Here's what we get for Jupiter, 24. It's bigger. I guess it's not obvious. Jupiter is heavier, but its radius is also bigger, right? So there are competing effects here, but it ends up that the mass wins out over the radius, and it's about 25 meters per second squared. I think it's just a coincidence, okay? But to 3 figures, the mean value of G on the Earth is exactly this answer, to 3 figures. And I think that's just a coincidence. And in fact, we know it's a coincidence because you remember here, we expect, well, this is an average. Yeah, it's averaging. Yeah, you know, there's a systematic error here in our theory. It's due to actually these effects here. Okay, let's just focus on this one. Here, because G can actually be greater here, but G is systematically less. The actual G, little g, is systematically less by 1/3%. And so this, I think it's just going to be a coincidence that this happens to agree within three figures here. I'm pretty sure of that. On the other hand, the actual value of G on Jupiter is 22.9, significantly less, and it's due to these two, the oblateness and the spin. And you can see the deviation here is, let's see, this is about 23, this is about 25. So they deviate 2 parts in 25. That's 8 parts in 100, that's 8%. So there's an 8% deviation here for Jupiter. Okay, so any questions so far? So we're going to do a, I don't know if you guys are going to like this, but we're going to ask a question here. As you go, if you're on the Earth here, we have about 9.8 meters per second squared acceleration due to gravity. As you get farther and farther away, G is going to get less, right? Obviously. So how high do you have to go, roughly, to have a G decrease by 1%, a relatively small decrease in G? How high do you have to go? That's the problem. So here we can mathematically state this as follows. Here's G, this is G on the surface of the Earth. I go some height, this is what we're after, and I want G to be 1% less. So we've now reduced it to these 2 equations that we need to solve. And you can all do this, you can all solve it exactly or to high precision. But we're just after a rough estimate here. So I'm going to use this opportunity to discuss approximation methods. So this is going to look a lot more complicated to you than just how you would normally solve this. But this is the way, when people get more deeply involved in science and engineering, you realize that everything is an approximation and you want to approximate. It makes your life much easier. You understand things better. The problem a lot of times with introductory physics is everyone wants to solve things exact. They think everything's exact and we can solve things exactly. I went through this. I think everybody goes through it. But eventually you realize that you've got to make approximations. For example, in my modern physics course, I've told the students repeatedly in quantum mechanics, there's 3 problems you can solve exactly. Particle in a box, the hydrogen atom, and what's the third one? Anybody? A harmonic oscillator. Yeah, you knew that shit, right? So that now you don't know what I'm talking about, but that's not important. I'm trying to convey this thing to you. You know, there are 3 problems, so you learn very quickly to make approximations. It's just part of life. Okay, once you get beyond the introductory level. So that's sort of a little motivation here. So first of all, we need to simplify this. We don't care G, M, this G, we don't care about that. So let's just take the ratio. This is one way of doing it. Take this and put it underneath here. Take the left side here, put it underneath there, the right side there, put it underneath there. And that we get this equation. Okay. Now I'm going to go dimensionless here. That usually simplifies things and makes things more transparent. I'm going to take this r squared and put it underneath there, and I get this. And now, I don't think we've done it before in this class, but tell me if you guys have seen this before. 1 plus a small quantity. If the magnitude of this is much less than 1, okay, and you're squaring it, it's approximately 1 plus twice that quantity. Have you guys, anybody seen this before? Yeah, this is amazing. This is really useful. We use it all the time, you know, when we have small effects and we want to calculate and transparently see what's going on. So I'm going to replace this with 1 plus 2h over r. Also, look at this. This is going to look strange to you. This is going to look crazy. 1 over 0.99 is 1 over 1 minus 0.01. Anybody have any trouble with that? That's okay, right? Now, there's another approximation that we use all the time. 1 over 1 plus a small quantity is 1 minus a small quantity. And if you don't believe this, you can actually punch it in on your calculator. You'll see it's a good approximation. And the smaller epsilon is, the smaller the magnitude of epsilon, the better it becomes. And for our purposes, that's fine. So we make that approximation. On the left hand, we have approximation on the right hand side. We make this approximation here. We cancel the 1s, cancel these 2 1s, and here's what we get. And now we can solve for h, and the way I will add on to here the fact, the way that we would think about this and state it is h is equal to 0.5%. That's 0.5%. So h is pretty small compared to r for g. You know, we'd expect it to be small, but this actually quantifies it. So you have to go, how high is that? Well, you can work this out. Substitute the radius of the Earth. It's about 100,000 feet. About 100,000 feet. So, I don't know if you guys know this, but it was, when I was young, this was a big deal. The 1968 Olympics were in Mexico City. You've probably heard of the It was famous for several reasons. One of them was this guy named Bob Beamon just jumped like a foot farther than anyone had jumped, long jump before, a big distance. So people tried to explain it away by saying, oh, Mexico City is high, I think. Is it a mile high? Yeah. It's like Denver, okay. G's less. You know, gravitational. That doesn't account for it. But a lot of people bought that. I remember at the time. A lot of people said, oh yeah, it's qualitatively correct. But quantitatively, it doesn't look good, right? Because you got to go 100,000 feet, many miles, okay? It doesn't look good. Now, but there's another effect. What is it? How when you go higher up? Less atmosphere, less drag. Could be less drag. And I don't know what happened there, and I didn't look it up, but it's probably in Wikipedia somewhere. Okay, people didn't analyze this because they wanted to try to explain it away, but apparently it just it was just a freak of nature that this happened. This guy just, and I think before that he hadn't jumped that far. I don't know the history, but anyway. Okay, so now, any questions or comments so far? Okay, so how do you measure big G? You might say, well, oh, just look at planetary motion. Big G is in there, so you got to know the masses of the planets. How do you get the masses? How do they get the masses of the planets? Well, they get it by knowing big G. So you got to do, to get big G, you got to measure it in the laboratory, as far as I know. So, there must be other ways of doing it, but I don't know. Okay. A question or comment? What?
What you were talking about earlier, how do you get the mass of the Earth?
Yeah. Now you realize. Yeah, there's this famous story here. That's where we're headed. Okay? With a demonstration. Right? Okay, so here's the idea. And the person who first did this was Henry Cavendish, 1798. And I think, I didn't check this on Wikipedia, but I think it took him 10 years to do this experiment. He did it at home. He had to cut a hole in his ceiling. Why did he do that? He had a torsional balance, okay? Oh, and I think he funded himself. I think he didn't have to. It's always nice if you can do it, right? So he had a torsional oscillator. Here's a torsional oscillator. Now I have things in the way here, but can everybody see this? Can everybody kind of see this? What it is this. We have this bar here with it's a dumbbell, okay? And when I angularly displace it and let it go, it oscillates. It oscillates because there's torsional stiffness here. This fiber, in this case it's a wire, wants to return to equilibrium. It's a lot like a spring. In fact, there's a spring constant here. It's called the torsional constant. And so here's the idea. Imagine these two big masses here aren't there. Move them away, okay? There's going to be an equilibrium here, right? So here's my torsional oscillator. It's in equilibrium, right? Now I bring up these two big masses. What's going to happen? So this is going to rotate this way, but it's just going to be a little tiny bit because this is not an astronomical body, okay? The force is very weak here. But in principle, it will rotate this way, right? Does everybody see that? It's going to rotate this way. So the trick here, and it's a very simple trick, and people have used it in not just in this situation, but many situations. It goes by the name of an optical lever. If you bounce light off a mirror here, and you have this screen, the farther away you put the screen, for a little change in angle here, the farther away the screen is, the bigger distance it is on the screen, right? It's kind of like optical lever here, as opposed to a mechanical lever where you can lift something heavy, right? That's kind of the idea. The longer the the closer the fulcrum is to the end here, the more weight you can. We didn't talk about this, did we? But that's a mechanical lever. You get a mechanical advantage. Here there's an advantage. It's more sensitive here, this measurement. So what you can do here is, by varying the distances, you can actually verify the inverse square law. And if you know the distances here and you know how much it's rotated, you can find big G. You can find big G, and that's what Cavendish did. Let me see if I'm missing something here. Okay, so let's now look at this demonstration, okay? So you've seen this is the torsional oscillator, right? So Cavendish didn't have this, but we have a really nice light sources now to do this. It's a laser. So this is a laser pointer. It's been modified so that I can keep it on. Usually there's a momentary switch, right? So we defeated that. So, all right. So what you saw before was the laser light's bouncing off the mirror.
Watch your eyes.
And you can see, oh yeah, well, it's moving. It's not going to be okay. It's huge. It's huge. Let's go to smaller amplitude here, okay? Go to a little smaller amplitude here. So you can see, Jeannie, can you pick that up? Good. So you can see here, I knew that. I didn't have to ask that. At the end of the quarter, I'm asking if you can pick up something on that board when I know I've written on the board. Sorry. Okay, so you can see the amplitude of oscillation here. It's not very big. And we got this, well, I hit the table, do you see that? We're getting a rocking up and down. See, there's a rocking motion there. Okay, so let's go to a smaller amplitude. Now, eventually this is going to come to rest, right? So ideally, what Cavendish, this is one of the things I'm sure he found out, is, oh, why did he cut the hole in the ceiling? No, he wanted to make, the longer you have a fiber or a wire like this, the longer it is, the easier it is to twist. You're spreading out that stress. That torsional constant goes down. So the stiffness becomes less and less. That's why he cut. Now, I don't know if I read that or heard it from somebody, so it may not be right, but it sounds good, right? And you can just imagine how his wife felt. All right? Okay. So, anyway, one of the first things when you work with a torsional apparatus like this is that you would like for it to come to equilibrium, right? Good luck. It's going to take a long time. See how this thing oscillating? So what we're going to do is just draw the extreme points here. So it's going roughly between there and there. So equilibrium is going to be halfway, right? So now, it's a 5 kilogram slotted weights. You don't want to use a little weight hanger for this. Right, you're going to break it. So there are big weight hangers that go along with this. So I'm going to do this now. I'm going to put the mass here, similar to this kind of arrangement. I'm going to put one mass here, and I've got another one here to double the effect. Okay, and let me kind of stabilize it, keep trying to get rid of these. Okay, so now, right about there and roughly there. Yeah, that's close. So there's a deflection. You know, just you look at the average here if you like. You see that it's deflected. So it looks good, right? There's a little bit of a problem. It's deflected that way, right? It's deflected that way. Anybody see a problem here? So before we put the masses in, it was here. After we put the masses, it's here. So it's deflected this way. What's the problem?
It should deflect the other way.
Yeah, right. That's right. It should. So I guess we've stumbled onto anti-gravity, so patent, paper, Nobel Prize.
Nobel Prize.
Yeah.
Share the prize money with this whole class.
Of course. So what's the problem here? First of all, the gravitational force is extremely weak. There's no way you're going to see the gravitational force with this apparatus. It's just way too weak. Okay. But the fact that there's a problem here, you can see. Why did this shift down? Well, this is not that sturdy. This is kind of a flimsy table, right? This is called an AV table in schools. Audio visual, they used to. I don't know, I guess times have changed, but when I was a kid and they showed 8mm movies, they would put the projector, never mind. Okay, so what's happening here is, we're up, this is pretty sensitive. We have this long optical lever here. We're upsetting this thing. It's changing the levelness of this thing with these weights on here. That's why it dropped down. I think it's, so, this is not, we're not seeing anti-gravity here. Be nice, but let's see again. Now, so this is what Cavendish did, and again, it took a long time. This is painstaking. And he came up with a fairly accurate value for G, okay? I can't remember how accurate it is, but it was fairly accurate. And he was highly motivated to do this. And then it's afterwards that you find out what a lot of his motivation was. He didn't stop with just measuring big G, okay? He applied it. And this is what you guys were recognizing, I think. Here's our formula, right? Now that we've measured big G, what can we do with this? If you know The radius of the Earth. And the ancients knew, do you guys know this? Ancients knew, had a value for the radius of the Earth.
The ancient aliens.
Yeah, they had a much better value, and they passed it on. No, this was done in Egypt, but I think a Greek did it. I can't remember. Yeah, a Greek did this. So here's the Earth, and here's like an obelisk or something, okay, or something, just something that's going to cast a shadow on the same longitude. All right. So here's the sun. The sun is shining light here. You're going to get a different shadow. You're going to get more of a shadow there than here. Right? So if you do this, measure the shadow at when the sun is highest in the sky at noontime, and you compare the difference in the shadow, you can get the radius of the Earth. Eratosthenes or something did this, and thousands of years ago, several thousands of years ago. So, and there's other ways of doing it. Galileo noticed, I think it was Galileo who noticed, he was looking at ships on the sea, and it was calm, and the weather was good. And when he saw these ships coming in, what do you see first?
The mast.
The top of the mast, right? So, you could that's one way of determining the radius. You get some information on that, quantitative information. So, you can solve this for M. And he got this, I think, is the current accepted value to 3 figures, but he got very close. I think I'm using here the accepted value of G. He was a little bit off, but he was pretty close. So he is called the first person to weigh the Earth. He weighed the Earth.
Did he get a Nobel Prize?
They didn't have the Nobel Prize back then. But I would think he should have. No, they have a strict rule about that, right? The Nobel Prize? Okay. Now, he didn't stop there. He said, well, I can find the average density of the Earth. Total mass, that I now know, divided by the total volume, which you can calculate. And look at this, 5.5 grams per cubic centimeter. See, what do you think about that? Water, density of 1 gram per cubic centimeter. Dirt, rock, and all that is actually roughly 3 grams per cubic centimeter. So what did he infer? There's got to be stuff deep down in the Earth that's a lot more dense. And he was exactly right. He didn't know what it was, but it's iron, predominantly iron. There's a lot of iron down there that's much heavier than that. A remarkable achievement. Remarkable achievement. Anybody have any quick questions?